Earthquakes strike without warning, causing billions of dollars in damage and taking countless lives every year. And it's not just buildings that collapse. Bridges, hospitals, and public infrastructure are also at serious risk. Some of these structures have stood for decades, even centuries, but when the ground shakes, how many of them will survive? Beyond their structural importance, many of these monuments carry the history and identity of a nation. Losing them to an earthquake wouldn't just mean the destruction of a building, it would mean the loss of a cultural legacy that should be preserved for future generations. Assessing aging structures is not straightforward. Over their lifetime, they have endured harsh weather conditions, temperature fluctuations, environmental stress, and past earthquakes, each contributing to hidden damage that weakens their structural integrity. Should we just sit back and wait for 50 or 100 years until they naturally deteriorate so we can study them in a lab? Of course not. These structures are continuously degrading, gradually losing their strength and silently compromising the resilience of our critical infrastructure. Instead of waiting for structures to age naturally, I use cutting edge simulation techniques in my research to artificially age concrete structures in a virtual environment, replicating the cracks, weaknesses, and imperfections that develop over decades. With this approach, I can accurately predict how historical and aging concrete structures will behave during an earthquake before disaster strikes. But identifying vulnerabilities isn't enough. We need solutions. Many of these structures require modern reinforcement strategies to remain safe and functional. One promising solution is shape memory alloy, SMA material. SMAs are materials that have kind of a special power. When you bend them, they don't stay bent, they remember the original shape and return to it after deformation, somehow similar to a rubber band snapping back after being stretched. By integrating SMA material into reinforced concrete elements, we can enhance the resilience of structures, particularly by confining critical components like bridge columns. This can reduce damage and enhance the behavior for next extreme events such as earthquakes. My research focuses on developing advanced computational models to simulate how these retrofitting techniques influence the behavior of reinforced concrete structures. Earthquakes will continue to strike without warning, threatening lives and the structures will depend on. But with innovation and smart solutions, we don't have to accept devastation as inevitable. By strengthening aging infrastructure today, we ensure that when the ground shakes, our structures withstand, protecting communities and preserving history for future.